I mean, one of them was lectures given some elsewhere. And initially my plan was to cover both surveys. It turns out that I covered like, 10% of the first survey, or I don't know. Anyway, I recommend, the things that we did here, I recommend you take a look at my GIT with a twist survey. So that one is kind of the same style as we discussed here, and should be used as a guide to more advanced, more specific references. And what I'm talking today, this is the second survey, and I will just scratch the surface. But anyway, for today, I recommend also, there is the survey by Gerard Alper and David Hyon, which is, GIT constructions. The title might not be exactly correct, but you'll find the paper, GIT constructions for moduli of curves. So the goal is to construct the moduli space of curves, and let me start just recalling that C is a stable Deligne-Mumford stable curve if and only if C is at worst nodal and every P1 component and every rational component has at least 3 mark points. So a remark here, C is DM stable is equivalent to saying that C has nodal singularities and the dualizing sheaf is ample. This is kind of easy to see because you see that the dualizing sheaf, the canonical sheaf on P1 is O of minus 2. So unless you have at least 3 points to increase this, the dualizing sheaf will not be ample. And in general, you have this implication. So omega C ample implies automorphism of C is finite. So in this kind of situation, so for curves, and you have to be careful because this is kind of like a bad definition. So for curves is true also in the opposite direction. Of course, C nodal. Okay, so our goal is to construct MG bar. So MG bar, as I discussed from the beginning, should be the Hilbert scheme of C embedded by the pluricanonical in a big space modulo PGL and mu plus 1. And of course, here you might need to take a locally closed subset and stuff like that, but let's ignore that. Okay, or actually, it is preferable to work with the Chow variety. So Chow variety embedded here in the same way. There is, of course, a Hilbert to Chow morphism, and this one is actually better in this type of situation. But anyway, kind of the main theorem here is that MG is the GIT quotient as above for Hilb or Chow for mu much larger than 0. in fact, mu greater equal 5 suffices. And this is Mumford and Giza curve. So I will sketch the proof of this one without any kind of real details. But it turns out that we cannot do it by GIT. We cannot do it by pure GIT. So what do I mean by this? We need the Deligne-Mumford construction first. Actually, nowadays, so recently, I don't know what recently, last decade, I think pure GIT was done by Jun Lee and Xiaowei Wang. But the proof of Mumford and so on, it's actually done by using the Deligne-Mumford first. So let me say something. So GIT is a global construction. We have all of moduli, but we also have a local construction, which is basically, this is what was discussed like previous lecture. So just by general nonsense, like locally near a curve C, the moduli space is just deformation of C modulo the automorphism of C.
That's in the algebraic theory or in the analytic theory?
I will say so. I will say in a minute. So for the moment, for the moment. So just by thinking, so this is basically that. So the idea is, and I mean, so this was probably Deligne-Mumford 69, was why don't we glue these local deformations? And to kind of emphasize this, I'm getting mg bar. And the glue of local deformation, I know some people will kill me for this, but okay, it's like that. This is glue the local deformations. And the gadget here and the gadget here is what we will call the moduli stack. So this is a structure. This is basically exactly kind of this type of structure. This is a more general structure than scheme under kind of finite automorphism situation. When we call it Deligne-Mumford, you can imagine the Deligne-Mumford stack is just glue some smooth space modulo finite group. I mean, S is not necessarily, but the point is that the stack remembers the group. That's kind of the main difference. I don't remember what they did in the time of Deligne-Mumford or stuff like that, but let me state the result. So theorem, Thiel and Mori, maybe 90s or something, is that for any Deligne-Mumford stack, there is a coarse moduli scheme, moduli space, which is an algebraic space. So basically, if we have mg bar, this is what Deligne and Mumford constructed, then you would get mg bar at least as algebraic space. And this is basically, for our purposes, you can think of it as scheme. It's not quite the same, but anyway. So here is that, and this is kind of whatever. You can view this one as some sort, you can think of this one as also some sort of orbifold. Meaning kind of the data. So I mean locally, kind of locally, mg bar is just kind of c to the 3g minus 3 modulo a finite group, which is the automorphism of a curve. And we discussed that this is kind of whatever, these have quotient singularities. And we did an example like last time. Now, this is an important point that was raised, is that this gluing is in the best words in the étale topology. You might actually need also some sort of flat topologies actually, or things like that. So it's rather analytic or whatever, like the algebraic analog. Why is not in the Zariski topology? Because the Zariski topology is too coarse, and whatever, an open Zariski remembers the Kodaira dimensions and stuff like that. Okay. So now you note that deformation theory tells us what? So tells us that this stack mg bar is smooth. This is equivalent to saying for a nodal curve C nodal, the deformations are an obstruction. And it tells also that the boundary is normal crossings. Why is that? Because if I have a node, the deformation looks like this. So one node, so this is one node. This is the smoothing is a divisor. Smoothing gives, like the discriminant is a divisor. And if I have any two nodes, I can smooth them independently. So I get like a normal crossing situation. So these are in some sense local properties which are given by deformation theory. The main theorem of Deligne and Mumford is that this mg bar is a proper and in particular separated stack. I mean, we also know the automorphisms are finite, so Deligne-Mumford stack. And this is proven, so this is like a global property. This is proven by using the evaluative criterion of properness and semi-stable reduction. In the sense of curves, not GIT. So basically what it says, let me spell it out here. Is that if I have a family of curves over the puncture disk, then I can extend it to a family such that, I mean, after base change and so on, such that C0 is DM stable. So this is the evaluative criterion of properties. And I don't know if this was done, but probably this should be done in tutorials, why you can do this and whatever. That's an interesting thing. So let's go back to GIT. So as I said, that we embed omega c to the mu to p and mu, and we are taking, say, Chow variety. I will discuss what's kind of Chow versus Hilbert and stuff like that in a few minutes. So for now, you just take the Chow, which means that you are simply viewing as a cycle. You forget any kind of scheme structure that's associated in the Hilbert scheme thing. Anyway, so you get something like this. So Mumford, I guess 65, maybe 64. This is why he wrote the GIT book. He proved using numerical criterion that C smooth is stable. I mean, it's an oversimplification, but we did last time. I mean, yesterday in the tutorial, we discussed, for instance, that a smooth cubic is GIT stable. So basically, what you have to do is, no matter what one parameter subgroup you take, if it's negative, so basically what you show here is that for any lambda one parameter subgroup of G, which is SLN, if mu of C and lambda is less equal to 0, this means not stable, then it implies C is singular. Remember kind of the diagram from yesterday. If you impose this kind of less equal to 0, it means all kind of the monomials or whatever you do, all the characters of the representations are in a half plane, and then you see that some monomials are vanishing, and then it forces you to be singular. So this means the counter positive of this one is that if C is smooth, then C is stable. So this was before Deligne-Mumford. So we get that Mg is quasi-projective variety, and also kind of a good moduli, if you want, good moduli. Because kind of the stable locus, I mean, this is included in the good quotient in kind of when you have the stable locus modulo, the Chow stable things modulo the SLN. You would like to do the same thing. You would like to do the same thing for semi-stable curves, but unfortunately, this doesn't really work. I mean, now, as I said, Jun Lee has a method to prove it directly, but so cannot do the same for DM stable curves, meaning nodal and whatever curves. So what Mumford and so the solution is as follows. So in step one.
So when you say cannot do the same, they are not stable?
No. So you want to prove that if mu of x of C and lambda is less than 0, then it forces, so this means unstable, then it forces you C is equivalent to say, so for all lambda, C is not DM stable. So you want to say that.
Do you think this is not true?
No, it's true. But you cannot do it directly by using the numerical criterion. You can actually do only one direction, and this is kind of the step one. And let me comment here. It is easy to show that something is unstable. Because remember the numerical criterion, let me put it here, is that kind of x in x is semi-stable is equivalent for all lambda mu of x lambda is greater or equal to 0. So to show that something is unstable, it suffices to say there exists lambda one parameter subgroup such that mu of c and lambda is less than 0. This is the negative of this one. But to show that something is semi-stable, you need to prove for all lambda one parameter subgroup such that satisfies mu CL lambda greater or equal to 0. So to show that something is unstable, you really need to get a one parameter subgroup that does the trick. But to show that something is semi-stable, you need to show that for any one parameter subgroup you have certain property. It's much easier to find that exist. So basically, in step one, Mumford shows, or Giesecker shows that if C is not DM stable, then C is GIT unstable. I have absolutely no time to explain anything concrete here, but the idea is that if C has a singularity worse than a nodal, then you find lambda concentrated, so let's see has a singularity P in C worse than nodal. You find a lambda concentrated at P such that mu C lambda is less than 0, so it implies unstable. Similarly, if C has a P1 with one or two markings, then again you find a lambda concentrated on this P1 such that mu C lambda is less than 0, again unstable. So now I don't have time to explain, but actually when you have a one parameter subgroup, what it actually singles out, it singles out a flag. So associated to a one parameter subgroup, you have a parabolic subgroup, which in turn singles out a linear flag, which in turn kind of whatever makes this, whatever you give weights and so on. Anyway, so the upshot is that if you have something that's not the Lin Mumford stable, then it's kind of easy geometrically to produce one parameter subgroups that destabilize the situation, so you conclude they are not semi-stable. So the hard part is to say, oh well, if I have a Lin-Mumford semi-stable thing, for any one parameter subgroup, the numerical criterion would be positive. Because whatever, who knows? I mean, it's very complicated, and I will not write down. So what we prove is that the semi-stable thing, so GIT semi-stable curves, are included in the Lin-Mumford stable curves. And now to finish it off, so you want, so the hard part is the other one. I mean, GIT hard. But now using the properness of GIT and the Lin-Mumford stack, this is easy. And let's give the proof. So first of all, let me put a key proposition. This is the GIT semi-stable replacement lemma. So I have X projective, G acting on X, and I'm considering the quotient X mod G. Assume that I have a family X star over delta star over the puncture disk such that, say, XT is GIT stable. Then, as usually, after base change, I can extend to X over delta such that X0 is GIT semi-stable, or I can even assume polystable. So I'm starting with a family of things, and this is really important. And I mean, so this is whatever kind of the key property that you use in GIT. So if you have a family which is, say, smooth, then you can always fill it in with something that's GIT semi-stable, and you can even assume that the thing that you put in is has a closed orbit. XT is the general fiber, and X0 is the special fiber. So you have a one parameter family.
I mean, you begin with saying X projective.
Shoot. Okay, sorry, okay, C star, okay, C over delta. Okay, you are completely right. And of course, kind of C of T is a point of X stable, and C of C0 is a point of X semi-stable. That's the statement. So X, I was using X with two meanings. So X is the whatever the parameter space where I'm doing the GIT, and then I'm taking the family. Is it clear now? So X is the parameter space. So say parameter space for curves. This is the quotient. And I'm assuming that each fiber is GIT stable. And after the base change, I can extend it to a family such that the central fiber is GIT semi-stable. So let's conclude the proof. So what do I want? I want if C0 is the Lin-Mumford stable curve, then C0 is GIT semi-stable. So why don't I take a smoothing? So I take C delta as smoothing. And then I erase C0. So I'm considering just the family over the puncture disk. So CT is smooth. So this means, in particular, GIT stable by Mumford, whatever, Mumford 65. But now by the GIT replacement lemma, previous proposition, it tells me that I can get a family, I don't know, C prime, let's say delta, such that C0 prime is GIT semi-stable. So after base change, I can fill in such that the new central fiber is GIT semi-stable. But now by the step 1, I know that C0 prime is DM stable. I already proved I want to prove the converse. But now, how do we conclude? So we conclude because we have C over delta and C prime. So this is the DM family, and this is the GIT family. And they agree over delta star. And now I have to say a keyword. What's the keyword? The DM stack is separated, which means that the families agree, which means that which means exactly that C0 is GIT semi-stable. And actually, wait a minute, I have one more thing to say. So I conclude at this point that Chow semi-stable is the same thing as DM stable. And now what I conclude is that this is actually the same thing as Chow stable. Why is that? Because I know that semi-stable is the same thing as stable curve. In particular, it implies the automorphism group is finite. If I have such a situation that for all C semi-stable, the automorphism group is finite, then it implies all orbits are closed in the semi-stable locus. Because you see, the failure of an orbit to be closed is that I have a smaller orbit, so failure to be stable is that I have a small orbit in the closure. But of course, this cannot happen because the dimension of the orbit is given, the dimension of the orbit is easily computed, is whatever the dimension of the group minus the stabilizer. So there are no small orbits. So because there are no small orbits, everything is stable. So the conclusion is that indeed I have mg bar is Chow stable, which is the same thing as semi-stable mod PGLN. And this is as good, so this is coarse moduli space, and this is as good as it comes. And so what I gain by this procedure so what is gained is that this mg bar is a projective variety, even normal projective variety. So before, a priori, I only knew that this is a proper algebraic stack. Now in modern, Kolar, which is whatever, late 80s, maybe even 90s. Now, you can get this without GIT. Meaning what you need here is to produce an ample line bundle on this algebraic stack, algebraic space, space on this algebraic space. But here the key is a properness, so you need key properness. So in particular, you have to go quite a distance to prove the original theorem of Mumford, saying that the smooth locus MG is quasi-projective. So there is no method to prove without GIT that MG is quasi-projective without using the compactification. Okay.
So the test work only characteristic 0, for example?
Okay, I'm characteristic 0 person, and I'll say something wrong if I try to comment on that. I mean, yeah. I mean, the Collar method definitely is only characteristic 0 because whatever you use MMP, but maybe, so of course the Lee-Mumford stack is over Z or something, and probably many things can go. Anyway, let me not go there. So there are two questions that should be raised. So two questions. If we are happy with this. So the first one is, what happens if I use C embedded omega C P and mu for small mu? And the second question, and I don't know, what happens in higher dimensions? And let me just, okay, it looks that I will have absolutely no time to say anything meaningful about the second, so let me just say here, let me say something in higher dimensions. So first of all, there exists a good analog of dm for varieties of general type and even log general type. This is the so-called Kolar-Shepard-Baron Alexeyev compactification. So if I start with, like, this is the smooth moduli, I mean, meaning the moduli of smooth objects, I can always compactify it, general type varieties. I can always compactify it by allowing X having semi-low canonical singularities. I think you'll hear about this next week quite a bit. And the second condition is some sort of dualizing sheaf, some sort of canonical sheaf. You have to make sense of this first, is ample. Semi-low canonical singularities, these are higher dimensional analog of nodal. So the point is that you always have these kind of two types of conditions, and this, as I said, implies in particular that the automorphism of X is finite. This direction is definitely not true in higher dimension. And so this one, there will be some sort of proper DM stack. Then, as I said, Kiel and Mori tells us that starting with this one, there is some sort of M bar, which is an algebraic space, and this is proper. And this is a coarse moduli space.
Is M constructed by GIT?
No. So this is like a stack. You just glue. And here, actually, this is a big warning, is that the global whatever kind of construction, I mean like stack and stuff like that, works. But the local picture, which is deformation theory, is Murphy law holds. So the upshot is that you need to choose carefully your example. But I mean, in some sense, I mean, you didn't do any, I mean, the only real theorem there is Kill and Mori, maybe, which is kind of, again, I don't know. So constructing like a stack is nothing. You just ungluing deformation, local deformations. So this is, so the first theorem is that you can always associate something that's an algebraic space if you start with a Deli-Mumford stack, not necessarily smooth. And then Kolar and Fujino, okay, they're not the same paper. They actually proved that M bar is a projective variety. And maybe here in the pair situation, I should put also Kovac, Patak-Falvi. So the upshot is that why do you need GIT and all of that? The upshot is that in terms of existence of a moduli space, it exists basically always, or whatever, as long as you are general type and stuff like that. The problem is, this is like a black box. You don't even know, EJ, what are the divisorial, what is the divisorial boundary? So you absolutely know, not even in codimension 1. And here kind of whatever, so one idea is construction by GIT might give you some insight. And okay, let me, so here you need to use asymptotic GIT, meaning that you embed X by big power of and try to do the same thing as for curves. Unfortunately, this is more subtle than for curves. Basically, there is no stabilization of GIT quotients. And for people interested in the subject, so for curves starting with the fifth power, you obtain mg bar. And the stability, as we proved, GIT semi-stability is the same thing as Kolar-Shepard-Bar, as the Lee-Mumford stability, which is the same thing as Kolar-Shepard-Baron stability. But here, as you go to higher and higher, you get only one inclusion. You don't get kind of the other inclusion, or even kind of a partial inclusion or something. So as you go to higher and higher, you always get a different set of semi-stable points. And there are examples of this type. And for references, you should check out Shenyang Xu and Wang, Xiaowei Wang, and the work of Odaka. And this is kind of related to the theory of K-stability. And I would love to talk about this one, but I'm really out of time.
Even if you fix a given modular space? No?
Yeah, no. You fix the moduli space, And the typical behavior is that as you go higher and higher, you get. So there are actually two good theorems here. Good theorems here. First of all is the theorem of Giesecker, which says that if X is a smooth surface of general type, then X is asymptotically stable. And then there is Donaldson.
Meaning what?
Sorry?
Meaning what?
Meaning that whatever, for mu large enough,
Okay.
larger than some n, X is stable for like chow X in Pn omega c mu.
So when n so this bound depends
On the moduli space.
on the moduli, so on the characters of x.
Yeah, so once you fix a moduli space, if you take the smooth surfaces of general type, then at some point, like this is kind of the theorem of Mumford, the smooth one. But the kind of the non-smooth one, when you go to nodals, it doesn't work, and there are examples. And also kind of Donaldson and Tian, or I don't know, so they should not be on the same line, but anyway, Donaldson, Tian, say that if X has special metrics, then X become asymptotically stable. But now kind of the issue again, you get into the singularity situation, because kind of is the issue, what do you do with the metrics when you go to degenerate surfaces and stuff like that. So anyway. So the upshot was that on surface, things work as for curves, but I don't know, the understanding, it is embarrassing if you try to do, I don't know, surfaces with, I don't know, there is no true example of compact moduli space of surfaces of general type, like an understanding what's that. All the examples that are known are coming from curves, whatever hyperplane arrangement, and whatever stuff of lower dimensions. Okay, so let me go back to curves. This was kind of question one. So what if I'm doing C omega C in Pn? And I'm trying to do GIT in this situation. So here you see I will miss out the hyperelliptic curves. So kind of the first, so in some sense I will say it, GIT kind of sees only linear properties of the objects. I mean, okay, this hyperelliptic case is clear, but you can say why not whatever mu equals 3 or 2, 3, 4 or something. But the point is that GIT only sees linear properties of the objects. So this means that whatever, so GIT detects like singular points, tangent things, tangent lines, tangent planes, and so on. It doesn't detect something more subtle, which is not linear. But of course, kind of, if I'm taking larger and larger embedding omega c to p and mu, this has the effect of linearizing C. Think about if I have xd in Pn, if I'm taking the Veronese d, then the Veronese of xd inside the Veronese of Pn actually becomes a hyperplane section. So I'm starting with a high degree something. If I do the Veronese, I'm getting a hyperplane section. This explains why kind of large mu are better. Because if I do large mu, I kind of linearize my curve. I will detect by intersecting, I will detect stuff about C in terms of intersecting with hyperplane and linear spaces, and then it will be detected by GIT. So let's see what's happening in low degree if I'm going to mu. So low mu canonical embeddings. And for this one, I need to define the so-called Hassett-Kiel models. And I will denote them by mg bar of alpha, and they are defined by proj of the ring of sections on mg bar lambda, canonical k mg bar plus alpha delta, where this is the boundary of mg bar. This is a canonical class. By MMP tells us that this is finitely generated for alpha in between 0 and 1. It is a basic fact which might have been discussed here, is that mg bar of 1, this is just kind of by definition, this is just mg bar. If G is large enough, I don't know, 23, 24 is suffices, then mg bar of 0, it is mg bar canonical, which means proj of the ring of canonical of mg bar. So this is the canonical model of the Deligne-Mumford compactification. So you need here, this I think was discussed earlier, so for G large enough, mg bar is general type, and then this kind of makes sense. But the point, so the point that we need to say is that I'm just defining this mg bar of alpha. The Hassett-Kiel idea was to interpolate from the low canonical model at 1 to the canonical model at 0. And the idea was to have a continuous interpolation given by alpha in between. Again, by MMP, we know that this behaves nicely as alpha varies analog to VGIT picture that we discussed. So there will be finitely many chambers. There will be mg bar, which is mg bar of 1. You go down, you go up, and so on, and flips. But the issue is kind of no idea of what models you get. Is the picture clear what I'm saying? So I'm just defining this kind of abstractly. I'm taking the ring of sections for this line bundle, the canonical plus alpha delta. And then I will get a number of models, and I'm going up and down and whatever. So there is some sort of flipping behavior and so on. But the problem is that I have no idea what are the next spaces and so on. And what was done, so here is Hassett, Hayen, Alper, Fedorchuk, Smythe, Hyon, Lee, and many others, is basically all the models that we know are obtained by GIT for small mu.
So you mean all the models that you know
In this thing. And actually kind of like the GIT models that occur, I mean, most of them are fitting in that picture. So the most famous example is that so the first birational contraction, birational modification occurring as alpha goes to 0 is at alpha equals 911. So basically in that situation one gets mg bar maps to mg 911. So first of all, let me describe it geometrically. This is mg pseudo-stable. So where pseudo-stable C is pseudo-stable means that C has nodes and cusps, nodes and cusps. So I'm allowing cuspidal things, but C doesn't have elliptic tails. So what is an elliptic tail is this kind of pictures. E, so this is elliptic. So I'm not allowing, I'm requiring that the elliptic curves have 2 points, 2 mark points on them. So this is pseudo-stable. And you see that all it happens here, actually this is a divisorial contraction. So basically the divisor, I think this is D1 divisor in mg bar is contracted to a codimension 2 locus, which is C prime bar or something. So the normalization of the cuspidal curve is C prime, and you lose the information of the elliptic curve. And what it has to do with the GIT, this is a theorem of David Schubert or so. Schubert, I mean not the Schubert calculus. So this was was in the 90s. Is that this is Chow 4 embedded C4 PN not SL, whatever it is. So this is what you get for mu equals 4. And then whatever so you have mg bar maps to mg 911, which is divisorial, and then there will be mg maybe 710, mg 710 minus epsilon. This is kind of the first flip. This is described by Hassett and Hyon in an honors paper. So it's an honors paper of them. And this is based on, I think, 2 canonical embeddings. I might be wrong, so I don't know, you have to, but just it gives you like a lower canonical embedding. So the first one is given kind of the bound from that. And this is kind of the maybe Alper, Fedorchuk, and Smythe maybe continue a bit more. At the other extreme, you can use GIT to completely describe the Hassett-Kiel in low genera. So in genus free is actually quite interesting. So genus free is easy. And okay, this is Hyon and Lee probably. In genus 4, this is quite interesting. And in particular here, one considers GIT for canonical genus 4 curves. What is a canonical genus 4 curve? This is a two-free complete intersection in P3. And here you should see my paper, Casalaina, Martin, Jensen, and myself. We are actually doing VGIT. So the upshot is, as I said, all the known models, all you can say concretely, so you have this big picture, this Hassett-Kiel and stuff like that, but basically concretely you cannot say, you can say very little about what are the steps and whatever. Maybe Alper and Fedorchuk and Smythe have some kind of alternative approach. But concretely, the most results that you get are doing various GITs, for instance, this kind of lower canonical embeddings and using Chow and Hilbert schemes and whatever. I would love to explain about that, but maybe it's better in private. So let me stop here.